Hosam is coming from the George Washington University, and he's a prominent statistician, and statistician not in the statistical physics sense, but a person who actually knows statistics. The dirty secret of statistical physics that we don't, right? We're just learning that we know probabilities, but not necessarily statistics to start with. And he has worked on a number of issues that pertain to our work, including the Poisson models, which is kind of like the mathematician's way of describing preferential attachment, right? If I think about that way, and recently he's interested. He was considering kind of spending some time in the lab. So we thought before that happens, why don't we have him and get to know him a little bit, and he gets to know us, right? So this is kind of an introduction both ways. And thanks for joining us for the time being. Okay.
Thank you very much for this introduction. It's a privilege to be here today, and I thank Albert for giving me this opportunity. I'll be talking about self-similar hooking networks. I'll explain the title in a few minutes. And this is your logo. I stole it from your website. Hey, it's a public image.
We're very open source here.
So the plan for the talk is I will introduce the self-similar networks. Then I'll speak about two models of randomness for the growth of these networks. A uniform model of attachment and a preferential attachment system, which is, of course, a big issue invented in the center and promoted. For good reasons, of course, because it does match reality in many cases. In this network, I'll be looking at local and global degree profiles. Jazz told me that the talk is 30 minutes. I'll try to stay within these boundaries. But of course, it's barely enough time to mention the results, especially that I have a number of them. So I will try to rely more on intuition in graphics for the message to come across. So I will discuss some exact results, and you'll see that Stirling numbers of both kinds come into the picture. Like the Stirling numbers of the first kind come with the uniform attachment scheme, and of the second kind, they do come with the preferential attachment scheme. These are exact, then we got into some asymptotics, and you will see a variety of different asymptotical results. So what is a self-similar hooking network? I have a graph, a starting graph. It's a connected graph, and it does have a special node in it called the hook. Many networks in real life grow by stringing together components that are similar. So it's like these are building blocks of a network. So at each stage in the growth of the network, a copy of the seed is obtained and hooked into the existing network. So at each stage, a node is identified as like the hooking node for the next copy. And of course, there is a question of how to choose it, and that's where the models of randomness come into the picture. So as an example, the graph at time 0 could be this. It's the seed itself. Then this might be the node chosen in it for connection. Then you bring a copy of this and you attach it, right? Then let's say in this network, you choose a node, possibly this one. So you bring a copy of this graph and attach it. And you keep doing this, and you will get a network, a random graph of a large size if you perpetuate this for a large number of steps. The interest in this is that it's a general model. So it's like many existing models do fit that more general framework. As an example, the Barabasi-Albert network is something very similar, where your seeds are just legs of length 2. So it's like one of the two nodes would be the hook, and the other one is just a leaf in the tree. Then, as you can see, copies of this come and attach themselves. So here's an attachment, then here's another attachment, and then the next one in this structure. happens to hit the root node and so forth. Of course, what makes Barabasi-Albert network a Barabasi-Albert is the model of randomness that you attach to the network, like the probabilities by which you choose the nodes. Another example of this would be a cactus graph. More generally, a cactus graph is a graph made up of cycles, not necessarily of the same length, but like to simplify, one particular interesting graph might be the one grown from like cycles of the same length, triangles, for example. So you can imagine that after a few hooking steps, you can get a whole bunch of triangles attached together. In the literature, this is called a cactus graph. So the scope of the study is to look into two types of two profiles of node degrees, a local profile and the global profile. So the local profile is like you track the evolution of the degree of a specific node. So here is a node that appeared at time j, for example. What happens to it when the age of the network is n much larger than j or even close to j? You will see some surprises. It's like, you know, for different j, you like, depending on the interplay between j and n, you get different results. So that would be a local attention to a specific node. Versus, for example, here's the network time n. It's a large structure. And I'm looking in this network for nodes of specific degrees. So it's like a raw count of how many nodes of any particular type.
That would be the degree distribution, right? You know, the global would be the degree distribution.
I suppose so, yes.
Yes.
So what about the results that you get out of this? Well, for the local case, I did mention that you will get Stirling numbers of the first kind. That's the one that appears in the uniform case. Then asymptotically, you find phase transitions or phase changes, depending on the relationship between the time of appearance and the age of the network. So the very, very early nodes, as we shall see, end up having a Gaussian distribution. Intermediate nodes, and that needs a definition, of course, have a Poisson distribution. And the very late nodes that come at the very end, they will have their degree, like their own degree, the degree they came in, without additions to it, without recruiting any additional nodes. In the global profile, we will find, I'll just tap into the results a little bit, and we will find multivariate joint distributions among the different kinds of node counts. A little bit of notation to ease our way through the discussion. You might expect that, like, I'm attaching graphs. So, of course, properties of the incoming graphs will affect the whole picture, will enter into the parameterization of the result. So, the graph, the seed, has like a set of vertices. So, I'm going to call the size of that set just little d, and it has a set of edges. I will call that eta. Then one specific parameter that will pervade several results is this little h, which is the degree of the hook itself. Okay? Technically speaking, you know, just for the proper setting of a probability space and whatnot, you don't have a seed, you actually have a sequence of seeds. Then you get a space built from like these components. This generalized harmonic number will appear in the final results. You are probably familiar with it already. If x is 0, you get a very specific number, which is like, you know, just the reciprocals. Especially when s is 1, you get 1 plus 1/2 plus 1/3, the well-known harmonic number. But there are generalizations of it, and that's the one that we'll need today. Other notation is needed, and it will come in time. No need to just, like, you know, overload uh, the discussion with notation at this time. So when I say I want to look at the local degrees, I have to have a mechanism by which I specify a node. So I'm going to come up with a labeling, any arbitrary labeling of the seed. In this running example, 1, 2, 3, 4, 5. Just to be a little bit systematic, I'm going to call the hook. I'm going to always refer to it as node 1. Other than that, everything is arbitrary. And I'm going to take this labeling as a canonical system, like other seeds that will come will follow the same labeling. So now you can see that like any particular node in the network, it appeared at a certain point in time, which I call J, for example, and it has its canonical labeling at the time of the appearance. As an example, I would refer to a node like this as the node that appeared at time 1, this is time 0. Time 1, so I need two components to specify a node. Time 1, and it's the force in the canonical representation. All right? So these are the two components. J is the timestamp, and R is the label in the canonical count. Since I'm looking at node degrees, well, the seeds, node R in the seed has a degree, and I'm going to refer to this with the notation D of R. Okay? Then I'm going to look at the local profile, as mentioned, and that is like for a node, JR, time N. Is the notation clear to everyone? So as an example, let's look at node 04 at time 2. If we go back to this graph, this is the graph at time 2, and that's the N, right? And it is node, what was it? We decided to look at 0, 4, yes. So this is node 04, the one at the period of time 0, and it's forcing the labeling. And that's like its degree at time 2. So it's like that particular degree is going to be 6, as you can see. Okay, so the network is growing. Nothing makes any sense unless you can't call it random unless you know what random means. So there are several models of randomness that can suggest themselves as natural. I just looked at these two systems. Of course, there's no reason why not study other methods of attachment, like attaching, for example, with a preference to younger age or older age, or like depth in the graph from the starting graph and so forth. But the usual term for like preferential attachment means, today at least, means this. Like you attach to degrees, but the rich get richer. Those who have many connections have a higher chance of attracting the next hook. Versus, of course, a simplistic model of uniform attachment. So just to give you a taste of all these types of results, I looked at the average node degree, and the node is specified by this timestamp, GNR, time N. And this is what comes out. I'm going to spare you all kinds of details of the proof and how it came about. I just solved some recurrence equations and I got this result. In this result, this is the harmonic that I mentioned earlier. And it's a generalized harmonic. This is the X in it. So that's what I need. Remember that this V is the set of size of the set of vertices in the incoming graphs. All right? So you would recognize right away that this provides me with different asymptotics. Even the average, we see different asymptotics. So it's like if n is very large, these harmonics grow like log n, and the role of hj is just like nothing, it's like that. lower order term that I can ignore. So at like n large and j fixed, however large it is, like j is 100, for example, but n is in the billions. So I will get a logarithmic expansion. If you are looking just at the dominant term, you'll see a lot. Versus, for example, if j is growing to infinity. As an example, I may choose an n, a billion, and they say, let me take square root of that. So it's like I may relate j to n and study the growth. So here, this harmonic itself will provide logarithms that will come into the asymptotics. Cannot be neglected. The same story repeats in the variance. When you study the variance, you find the same kinds of phase change in it. I worked through the exact distribution of the local profile, and it comes out giving you this lovely expression. As you can see, there are familiar things in it, such as Stirling numbers of the first kind. And these here are like the so-called rising factorials, like x times x plus 1 times x plus 2. So it's an expression. What's important here is that the k for which I can ask this question and get a non-zero answer has a form. And that form tells me that there are certain admissible degrees in the network. And that's to be expected, because what's the degree of a canonical, of any node? It is the degree that it came with, plus multiples of h, because every time I hit it with the hook, which has degree h. So these are, they define an admissible sequence of degrees. One thing I'd like to say about the graphs, let me go back here. Hook, node 1 appears only once in the network, whereas nodes labeled 2 can appear multiple times. Because every time you hit a node, it gets the hook gets subsumed in an older one. All right. So we have been discussing phases, and now it's becoming a little bit clearer that there will be early nodes with asymptotic average log n, and another phase at the early stage where j still plays a role. An example of this would be, for example, if j is asymptotic to 5 times n to the 3/4. So it's like the formula, the asymptotic formula has a log n over j in it. So it's like you would have an n over n to the 3/4. So you get somehow a force here, which is this. Whereas when you reach the asymptotic, when j is chosen to be linear in n, like alpha n, there's some alpha, strictly more than 1, the formula changes. There is no n in it anymore in the asymptotics. All right? And notice that I would consider this intermediate. Notice that alpha equals 1 has a very special role to it. When alpha is 1, this term is 0. Something like, for example, when can alpha be 1? When j is linearly dependent, like asymptotic to n itself, right? Something like this expression. Maybe asymptotic to n with some perturbation, like -5, minus log n, minus any little o n. In which case, you are going to get just the degree of the seed itself. Like the seed came, and it's very, very late. Its chance at recruiting anything in the future is zilch. So it's like it stays the same. Clear? Okay. We discussed just the averages, but you might expect that these changes will be reflected in the distribution itself. So it's like in the distribution, the asymptotic distributions, we will see phases. So once again, when j is fixed through some intermediate work, I don't have time to show you, I get a central limit theorem in the sense of like convergence in distribution to this particular normal. And as you might expect, the parameters of the incoming graphs enter into the parameters of the limit distribution. These are like, you know, the actual mean will be determined by H and V. In the like later early stage, I still get a similar central limit theorem, but like J cannot be neglected anymore. It comes into the picture, right? Then when I reach the intermediate stage, in which J is asymptotic to alpha n, I get the Poisson variable in the limit. And if alpha is 1, I get like convergence. It's actually this law is alpha equals 0, right? So it's like the Poisson becomes the 0 component. So I get just dr. But of course, like convergence in distribution is equivalent to convergence in probability when you converge to a constant. So you can claim that this result is upgraded slightly to something stronger. Okay. For the local degree profile, the parameter of interest to decide like the total affinity is the sum of all the degrees. So let me give this a name. If I call this muons of n, then by time n, I have been adding as like 2 eta at a time. Okay, it's twice the number of edges. The sum of all the degrees, twice the number of edges. All right. So it's like I've been adding linearly since time 0, that many. So the idea in preferential attachment is to say, well, let me condition on the information I have, on the network I have at this time. In the language of probability, you might choose to say condition on the sigma field generated by the first n-1 steps. So that's, think of this as the information. That's the shape, the form that we have. If I condition on that, then one of two things can happen. The incoming seed might hit the node I'm studying, or might like stay away. So if it stays away, nothing changes. If there's a hit, then its degree will go up by the degree of the hook, right? And the probability you assign or you attach to this is the degree itself. So given this delta, I can use it in my conditional probability. So it's like the probability of attaching to this node is its degree divided by the sum of all the degrees existing in the graph at this time. All right? And of course, this would be 1 minus that. So with this in mind, how do you study this? I suggest a study through polyr, so we map things on a polyr. I always use white and blue because I grew up by the Mediterranean and we have an affinity, a true love for the Mediterranean Sea. This picture, by the way, was taken in Egypt last summer, on the north coast of Egypt, and I took it myself. But today I'm going to make an exception because white doesn't show well on white. So it's like I'm going to use red. So I'm going to color my graphs with white and red. But what is it that I am coloring? I want to reflect the degrees, right? So the degree of a node is like, you know, half edge coming out of the node. So if this is the node of interest, then I'm going to color the half edges coming out of it with white, which is red today, and everything else with blue. And from here, I have a scheme. Like later hits. If I pick this node for attachment, then the degree of the hook will come and increase. Let's say the hook has degree 3. So its degree will go up by 3. So 3 half edges of the seed will become also red. And the rest of the seed, of course, is here. It's all staying away from this node and connected to other nodes. So that will be blue. But if the hit occurs at a node which is not the subject of my study, then I will just enrich it with blue nodes, and it's like the entire graph will add blue half edges. So your polyarm scheme, think of this as a scheme where these are like indexed by ball picked, and these are indexed by balls added. So if I pick the red, I add H red, and the rest, eta, is the total, like sum of the out degrees, the degrees of all the nodes, right? Twice the number of edges. So everything else is blue. Versus if I hit a node that's not the subject of the study, I will get just all blue. Okay? Once you set it up like this, you are falling back on the theory of polyarms. Polyarms with a zero at this point have been a challenge for quite some time. So it's like it wasn't until a very recent time that a few students of mine and myself came up with an explicit characterization of the moments of such a polyarm scheme. There are other earlier characterizations, not too many, but less explicit than this. So there was like a characterization by Flageolet and several other researchers before our time. So these are all the moments. I always find it quite remarkable to find a probability formula with alternating signs. What does that mean? It's like these are positive things, but somehow these numbers, like they coalesce together in such a way that you get exact cancellations that you always get something negative out of it. So in particular, the average, like that's when you raise this to power 1, will come out in terms of gamma functions, like this. Then if you study the asymptotics, in the same study with Pan Zhang and Chen, we like analyzed it asymptotically, and we got these gamma type distributions. They are called gamma type because the gamma function appears in them. Okay, so this was coming close to my time, and then I need a few more minutes.
We can always spend a few more minutes, so that's
Okay.
some flexibility, right?
So I promise not to overstay my just a few more minutes. So in the global profile, I need also a polyarm scheme, and the scheme will be different according to the attachment method. So if the attachment method is uniform, I'm going to color the nodes themselves, right? So for example, I may be looking at nodes of out degree 1 and 2 and everything else. So it's like nodes of out degree 1 will be white, nodes of out degree 2 are blue, and nodes of out degree 3 or higher will be red. Clear plan? If I am doing preferential attachment, then I'm coloring the half edges. So nodes of out degree 1, the half edge coming out of a node of out degree 1 will be red, the half edge coming out of a node of degree 2 will be blue, and the half edge coming out of a higher node will be green. I cannot use white here. It will look very off. We spoke already of admissible degrees, and I have to alert you to something. The seed coming into the graph has its own distribution of degrees. That doesn't mean that these are the degrees in the network, right? So the network has admissible degrees in it, and I can like order them in increasing order, and I can study any sub-collection of them. So I decided to look at just like to taste this kind of result, study the joint distribution of the smallest and second smallest in the network. All right? So of course parameters will come into the picture, such as how many of them are in each seed, how many nodes of this particular degree in a seed, because that will influence the ultimate result. Yes, I have a reason to have this particular graph. If this is my seed, the smallest degree that can appear in the whole network is 3. The second smallest is 6 if the hook matches an existing hook. So 6 is an admissible degree, D2 star, but it's not in the seed because the second largest in the seed has degree 7. Right? So with this in mind, 4 regimes force ourselves on us. What happens when I make these connections? Like, one possibility is the hook is the smallest, and 2H is the second smallest when I connect another hook to it. So that's one regime. They're not very much different, but you have to do things correctly. Versus, for example, the graph we looked at. The hook is the smallest, but when I add a second hook to it, I don't get I don't grow like the second smallest is not D1 star plus H. That's what I mean. Then, of course, the hook could be from the beginning the second admissible in the network, or could be higher than the second admissible in the entire network. With this in mind, you go and study these polyurns, like what happens if I add a node of this kind, the dynamics of the growth of the polyurn scheme, and each regime will give you a different growth model, right? So it's like then you are back into familiar territory. We have a standard polyurn theory that gives me almost sure results. So each scheme will have its own almost sure result. Let's take one of these and interpret it this like for the following. Let's say I look at regime 2. In this regime, the scheme gives me this almost sure law. Let's see why. Well, at each step, I am adding a copy of the seed. But the copy of the seed itself gets deprived because it gets attached to an existing seed. So consistently, there are n1 nodes of the degree of the seed in the seed. All right. So one of them gets lost systematically with each insertion. So I would expect that the number of nodes of out degree 1 in this regime, the seed has the smallest degree. So it's like I am linearly increasing the number of nodes of this, like the smallest degree by n1 minus 1. Whereas the second type of degrees is just systematically with each addition I get n2. So no deprivation is experienced with seconds. So it's like if you go through this, you will see that each of these makes perfect sense. The most complex is this one, of course, because of the interplay. The first degree comes up to the second degree, so the second degree gets affected by how many of them in the seed graph. You work through the theory of polyurns, and you get a multivariate central limit theorem. And of course, each regime will give you a different vector, mean vector, and a different covariance, limiting covariance matrix. Just to tap into a specific case to see the flavor of these results in a more explicit kind of representation. When you look at, let's say, the cactus graph that we talked about at the beginning, growing out of triangles, right? Things become a little bit more transparent when the graph itself has a structure, like a regular structure. So when the graphs are regular, like in this case, this becomes your specific Urn scheme, and the exact central limit theorem takes this form. It's an opportunity where you can figure out the exact mean vector and the exact covariance matrix. Something similar will happen if you study the global profile under preferential attachment. But of course, you would expect the numbers will change quite a bit.
Now you have many colors.
In the cortex,
Can I start with a question? So one thing it wasn't clear about this process is that is the model inherently deterministic or stochastic? Because I could imagine both, right? Say the BA model is stochastic, but we also have these, some of the models you showed remind me of some of the self-similar models that we often build, deterministic ones that create the scale-free network by repeating the same elements. And I was wondering, is that a different class or it could be?
I am not sure what the question is precisely, but like the network that grows out of this is random.
It's random, so because you're choosing randomly where you're picking
but
the
seed is one fixed seed.
I
Of course,
So
we can
loss is the same. Yes.
right. We can expand that to be you have a collection of seeds to work from,
Okay.
and even you could have a probability distribution on it if you wish.
What if you have
It could be,
recurrent
and
seeds? What do you have
it could be a
recurrent seeds?
generalization.
What do you have recurrent seeds? Like for example, one of the famous models that gives you a scale-free one is that you start a triangle and then you replace every link with a triangle, right? And then every link again with a triangle. So in a way you're hooking triangles onto the network. And it will be scale-free, but it's deterministic, right? And it has lots of interesting properties.
The edge that you are changing in the network is chosen randomly?
No, completely. Every single edge is maybe.
Oh, every single
So
edge.
in parallel, we replace everything. Now you could do it randomly, and you would probably get the same degree distribution and stuff like that. But the beauty is when you do it deterministically. So that's why. So I understood the randomness, but can you, if you were to do it deterministically, would you be getting, or would
It
that
might be a
be?
little parallel to chronic carrier graphs, right?
Yeah, I don't
So
know
it's
that,
like
but it's
matrix
you're doing it in parallel, right?
multiplication
At every step, every element is replaced by its replacement.
So you probably want one of two models. I have worked with something remotely similar some time back, and there was this, what I call the bursting argument. Like at the same time, every node, for example, bursts into a graph.
I guess that would be the equivalent, yes. The Dorobotsev-Mendez model would be something
Yeah.
like that. If every link is burst into a
Or
graph.
every edge, so that
Every edge is
it can
bursting.
happen at two different levels. Every edge suddenly becomes a different
Yeah, a triangle in this case, right?
graph.
So I have a question. So have you considered also like a distribution over the possible configuration that you are touching these kind of things, like with different probabilities, different geometric schemes to add there, like different geometric figures, like not just that specific subgraph, but another one, and then
Yeah, I
has
think
different
that's what we just
probabilities.
talked about.
Exactly.
You could allow your
Yes,
seed
exactly.
to be a collection of seeds.
Yes,
Maybe
exactly.
two. Like you have a choice each step of one of two seeds.
Okay.
You could even have a probability distribution on
Exactly.
that.
Yeah, I
Like
was saying
each
something
was
like
probably
that.
1/2, or
Yeah.
this one is more prevalent. So 3/4 this particular
So
shape and
mixtures in a certain
1/4.
way.
Yeah.
Yeah, that would be. No.
I haven't considered
Okay.
that, but it's a natural extension, I think.
No,
to this
and
work.
I mean, you know, we discussed about the knowledge graph. So the idea is that if you have in mind a way to grow the structure with specific modules that you are attaching, right, with a probability that is given, considering the fact that you are touching one specific entity or another one, that's what you're going to get, right, in a certain way. So, no, I was curious about this.
I think it's quite doable.
Yeah.
The mathematics will need some tweaking, but like it won't be much different. Yes.
So one thing that we were actually just discussing a few days ago is almost a reverse problem. You're given a graph and you're asked to infer properties about how it grew, knowing that there's some growth process. So let's say in this particular example, you're given a graph and you're given a node, and we'd like to know when in the process did that node, or was it likely that that node came and joined the graph, right? So kind of like, you know the degree, now can you infer the j of the time step that it came into being? Or
Historical perspective.
Very
perhaps
nice question.
you don't know the seed, but you know the resulting degree distribution. Could you infer the seed?
So I look
but
at the
degree
graph, and if I
distribution
see a
of the
node of degree 50,
seed? Yeah.
and the graph
size is, let's say, 5,000.
5,000.
What's the J of that
Exactly.
node?
What's the expected J of that node?
I see.
Would
I
it be very
have never
difficult
considered
to
something like this,
rework the
but,
framework
Yeah,
that you have?
but I think the result might be a mixture of
Mixture.
what's being.
Sure, if
Yeah.
it's growing, depending on the which regime you're kind of in.
Yeah, you're
Right.
gonna definitely have a guess, right, depending on.
But, I don't know, it should be a superposition of the different distributions of.
So for example, you might
possible
think of,
degrees.
instead of delta n and j, or j and n, the way it was written, random j and fixed n.
Mhm.
And that would be a mixing of the results that I got on a fixed j.
Right,
Yeah. Mixing with the probabilities you have in mind.
with the, right,
Yeah, I think so.
so you think you could work that back out?
I'm not sure without like sitting down and sweating
actually
over it for
Yeah.
several hours.
Because I think it could be a cool problem. The context we were discussing this in was in terms of network archaeology, is what they call it, right? But you have a protein interaction graph, and you want to know which were the original proteins that started it in evolutionary terms, and then there's some process that built up the relationships on it. So could you identify, for example, the original seed of the whole network?
Good question, of course.
That paper.
Yes, exactly, that paper.
Okay. Cool. Any other questions before we get a solution to this question? If not, thanks again for that.